Today we're going to be talking about parabolas. We've already discussed parabolas that have an orientation of up or down, and we're going to kind of extend that right now to deal with parabolas that are not necessarily functions, and we're going to really talk about them in terms of a conic section. Here are some parabolas that you would see in structures, so it takes a lot of engineering to make sure that these are as they need to be. Here is a conic section graph. It shows you the different ways that you can slice two cones, one inverted under the other, and it just depends on how you slice it. If you were to look at the face of that, you would have a different conic section. And parabolas then, you can see, are sliced not vertically up and down. If you were to slice it, you would only go through one of the cones. Here's another representation of conic sections, and this one I almost think looks better. You can see in the first diagram that you have the slice coming through only one of the cones. In the second one you have a circle which is parallel to the base. In the third one it does not go through the base, so it's like a circle except that it's not parallel to the base, so that is an ellipse. And then the third one, if you slice vertically through both cones, that is called a hyperbola. But today we're just going to deal with the parabola only. By definition, a parabola is the set of all points in a plane that are the same distance from a given point, called the focus, and a given line called the directrix. So what this means then, and you can see it more clearly on the second figure, is that if I were to go from my focus to any point on the parabola and then drop straight down, meaning perpendicular to the directrix, these would have the same length. And if I have an infinitely many of them, and I were to do this to make sure that these have the same length, then these points then form a parabola. Here's another representation of them. You can see that in the previous slide we had a parabola open to the right, and in this slide we have a parabola open up. Same definition, from the focus to any point on the parabola, or straight down to the directrix, perpendicular, those would have the same distance. So if we look at an equation that's in standard form, y equals 2x squared plus 12x plus 14, if we want to put this in what we call vertex form, we know that we complete the square. So when I look at this, I've already gone through this process before. I'm going to move the 14 over. We know that we can't complete the square unless the a value is 1. So I'm going to divide here. So I have y over 2 minus 7. And I know that I have to do some work to come up with a complete square. So I'm going to add some blanks. Just to review, I take half of b and square that. Add to both sides. If I clean up this side, I have y over 2 plus 2 is equal to x plus 3 squared. This is what I was going for, this perfect square. That was the whole point of doing this. I'm trying to get it into vertex form right here. So then I just move some things around so I get it in that form. So if I subtract the 2, I have y over 2 is equal to x plus 3 squared minus 2. And then I need to multiply by 2, so I have y equals 2, x plus 3 squared minus 4. Here is my vertex form. My vertex then is -3, -4. It is y equals this quantity, so it's going to be open up or down, and specifically up because my a value is positive. My axis of symmetry is x equals -3. So I go ahead and graph my vertex at -3, -4, my axis of symmetry, and then I recall back to the parent function. The parent function graphs the relationship 1, 1, 2, 4, because if I have my parent, which is y equals x squared, my vertex is at 0, 0, I go 1 away, 1 up, 2 away, 4 up. But in this case, my a value is 1, so I'm changing that by a factor of 2. So instead of going 1 away, 1 up, I'm going to go 1 away, 2 up. And instead of going 2, 4, I'm also going to take that times 2, so I'm going to go 2 away and 8 up. So I have my parabola.